Welcome students in the lecture series of some basic concepts of real analysis. In the previous lecture, we discussed about squeeze theorem, geometrical interpretation of squeeze theorem, square root theorem for sequences, monotone sequences theorem, monotone convergence theorem, geometrical interpretation of monotone convergence theorem, and subsequences and divergence criteria. In today's lecture, we will discuss about Cauchy sequences and their properties. Now, let us start with our first result. Our first result is monotone subsequence theorem. Monotone subsequence theorem states that if x is equals to xn is a sequence of real numbers r, then there is a subsequence of xn that is monotone. I repeat, if x is equals to xn is a sequence of real numbers r, then there is a subsequence of x is equals to xn that is monotone. For that, let us understand the term peak. We say that the mth term is a peak if xm is greater than or equals to xn for all n such that n is greater than or equals to m. That is, for every term we have xm is greater than or equals to xn. That is, xm is never exceeded by any term that follows in the sequence. Note that in a decreasing sequence, every term is a peak term, while in an increasing sequence, no term is a peak term. So, let us start with the proof. We will consider two cases depending whether x has infinitely many peaks or x has finitely many peaks. Let us consider case 1. Our case 1 is, suppose there are infinitely many peaks in the sequence. Let x is equals to xn be the given sequence and x dash is equals to xn k be the subsequences of all the peaks the main sequence have. That is, each xn k is a peak and we have a sequence like this. The sequence is n1 is strictly less than n2 and strictly less than n3 up to so on. Then for any k, we must have xn k is strictly greater than xm for all n k less than m. So, we must have sequence of the form xn1 is strictly greater than xn2 and xn2 is strictly greater than xn3 and so on. Therefore, we can easily check the given sequence is strictly decreasing and hence monotonic. Case 2, when we have only finitely many peaks. Then if we have finitely many peaks, then after some index n, there are no more peaks. That is, for all n greater than capital N, where capital N is our natural number, xn is not a peak. So, for that there must exist n greater than capital N and small m greater than n such that we have xm is greater than or equals to xn. Now, we construct a non-decreasing subsequence. For that, let us start with the construction. Pick any natural number n1 greater than capital N. Since xn1 is not a peak, if xn1 is not a peak, then there exists some other natural number and say n2 which is strictly greater than n1 such that we have xn2 is greater than or equals to xn1. In similar pattern, we can say that xn2 is not a peak. If xn2 is not a peak, then there must exist some other natural number say n3 which is strictly greater than n2 and we have xn3 is greater than or equals to xn2. Continuing in this process, we get a subsequence of the form xn1 is less or equals to xn2 and xn2 is less or equals to xn3. So, this is our non-decreasing subsequence, hence monotonic. Hence, we can conclude that if x is equals to xn is a sequence of real numbers r, then there is a subsequence of x is equals to xn, say x dash is equals to xnk, that is monotone. Let us move towards our next result. Our next result is geometrical interpretation of monotone subsequence theorem. Geometrical interpretation of the monotone subsequence theorem for a real number sequence is to visualize the sequence's term as a point on a 1D number line where peaks represent points greater than or equal to all subsequent terms. I repeat, our first geometrical interpretation of the monotone subsequence theorem for a real number sequence is to visualize the sequence's terms as points on a one-dimensional number line, whereas peaks represent points greater than or equal to all subsequent terms. The theorem states any such sequence will have either an infinite sequence of decreasing peaks, or if finitely many, then an infinite increasing subsequence of starting after the last peak, ensuring the existence of a monotone subsequence in either case. Our next result is the Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem states that a bounded sequence of real numbers R has a convergent subsequence. I repeat the statement. Bolzano-Weierstrass theorem states that a bounded sequence of real number R has a convergent subsequence. Let us start with the proof of Bolzano-Weierstrass theorem. For that, recall monotone subsequence theorem. Monotone subsequence theorem states that if x is equals to xn is a sequence of real numbers R, then there is a subsequence of x is equals to xn, that is monotone. Let us start with the proof. Given x is equals to xn be the bounded sequence of real numbers, then by monotone subsequence theorem, which is we define above, we can say that the sequence x is equals to xn has a subsequence which is monotone. So, let us say x dash is equals to xnk be the monotone subsequence of x is equals to xn. As given, x is equals to xn is the bounded sequence of real numbers, and x dash is equals to xnk is a subsequence of xn, then we can say that our subsequence is also bounded. That means, x dash is equals to xnk is also bounded. Recall the next theorem, monotone convergence theorem. The statement of monotone convergence theorem is a monotone sequence of real numbers R is convergent if and only if it is bounded. Using this result, we can say that the subsequence is convergent, that is x dash is equals to xnk is a convergent sequence or convergent subsequence of x is equals to xn. Hence, we conclude that a bounded sequence of real numbers has a convergent subsequence. Geometrical interpretation of Bolzano-Weierstrass theorem. The geometrical interpretation of Bolzano-Weierstrass theorem states that if you have an infinite number of points on the real line that are confined to be finite interval, that is bounded, those points must clump around at least one specific point. I repeat, geometrically, the Bolzano-Weierstrass theorem states that if you have an infinite number of points on the real line that are confined to a finite interval, that means bounded, those points must clump around at least one specific point. This clumping is represented by a convergent subsequence. This clumping is represented by a convergent subsequence, which is an infinite subset of the original sequence that gets arbitrarily close to a limit point. Now, let us start with the today's topic. Our today's topic is Cauchy sequences. To understand the Cauchy sequence, let us start with the definition of Cauchy sequence. A sequence x is equals to xn of real numbers is said to be a Cauchy sequence if for every epsilon greater than 0, there must exist a natural number, say h, depending upon that epsilon, such that for all natural numbers n and m greater than or equals to h, the term xn and xm must satisfies modulus of xn minus xm is less than epsilon. I repeat the definition. A sequence x is equals to xn of a real numbers is said to be a Cauchy sequence if for every epsilon greater than 0, there exists a natural number h depending upon epsilon, such that we have modulus of xn minus xm is less than epsilon for all n and m greater than or equals to that natural number, and that natural number is depending upon the epsilon. To understand the definition, let us start with the example. First example is, we need to show that the sequence is a Cauchy sequence, and the sequence is defined as x is equals to 1 upon n square for every n belongs to the natural number. So, for that let us assume epsilon greater than 0 be given. As epsilon greater than 0 is our real number, so by the Archimedean property we can say that there must exist some natural number greater than this real number. So, let us assume that natural number is h, which is depending upon epsilon. So, we have our equation number 1. Equation number 1 says that h depending upon epsilon is greater than 2 upon epsilon. Our equation number 1 can be written as 1 upon h, where h is depending upon epsilon is strictly less than epsilon upon 2. Say this is our equation number 2. Then, if for all natural numbers m and n greater than h, we can say that m square is strictly greater than h as well as n square is strictly greater than h. Say this is our equation number 3. So, from equation number 2 and equation number 3, we can generate our equation number 4. Equation number 4 says that 1 upon n square is strictly less than 1 upon h, where h is depending upon epsilon, and this term is less than epsilon upon 2. This is our equation number 4. In similar pattern, we can perform this result for the value of m, where m is our natural number greater than h. If m is greater than h, then we can say that m square is also greater than h. Then taking reciprocal, we get our equation number 5, that is 1 upon m square is less than 1 upon h, where h is depending upon epsilon, and 1 upon h is strictly less than epsilon upon 2. Say this is our equation number 5th. Therefore, if we have natural numbers m and n greater than h, then consider the equation modulus of 1 upon m square minus 1 upon n square. If we apply triangular inequality in this, we get this term is less or equals to 1 upon m square plus 1 upon n square from the equation 4th and equation number 5th. The equation number 4th says that 1 upon n square is less than epsilon upon 2, and equation 5th states that 1 upon m square is less than epsilon upon 2. So, from equation number 4 and equation number 5th, we can say that this term is less than epsilon upon 2 plus epsilon upon 2, which gives us epsilon. This implies that modulus of 1 upon m square minus 1 upon n square is less than epsilon for all natural numbers m and n greater than or equals to h, where h is our depending upon epsilon. Since epsilon greater than 0 is an arbitrary number or arbitrary real number, we conclude that the sequence x is equals to 1 upon n square is a Cauchy sequence. Now, let us start with the next example with negation of the definition of a Cauchy sequence. Let us define the negation of the definition of a Cauchy sequence. There exists epsilon naught greater than 0 such that for every natural number h, there must exist at least one n greater than h and at least one m greater than h, such that we have this inequality. That means, modulus of x n minus x m is greater than epsilon naught. Let us recall the definition of negation of the Cauchy sequence. The negation of the Cauchy sequence is defined as there must exist some epsilon naught greater than 0 such that for every natural number h, there must exist at least one n, a natural number greater than h, and at least one another natural number m, which is also strictly greater than h, such that we have modulus of x n minus x m is greater than epsilon naught. To understand the definition of negation of the Cauchy sequence, let us start with the example. Our example is the sequence x is equals to minus 1 to the power n plus 1 upon n is not a Cauchy sequence. So, let us start with the solution for a given sequence. The given sequence is x is equals to minus 1 to the power n plus 1 upon n. We can easily check if the value of n is even, we have x n is strictly greater than 0, and if x n plus 1 is less than 0. If we take our epsilon naught is equals to 1 by 2, then for any natural number h, we can choose an even natural number, say n is greater than h, and a natural number m is equals to n plus 1. We get modulus of x n minus x n plus 1, which is greater than or equals to 1, and this 1 is strictly greater than epsilon naught because our epsilon naught is 1 upon 2. So, we get our equation modulus of x n minus x n plus 1 is strictly greater than epsilon naught. Thus, by the negation of the Cauchy sequence, we conclude that the sequence defined as x is equals to minus 1 to the power n plus 1 upon n is not a Cauchy sequence. Remark for that, we emphasize that to prove a Cauchy sequence or to prove a sequence is a Cauchy sequence, if we may not assume a relationship between m and n, since the required inequality must hold this condition. That means, the required inequality modulus of x n minus x m is strictly less than epsilon must hold for all natural numbers m and n which are greater than or equals to h. But to prove a sequence is not a Cauchy sequence, we must specify a relation between m and n as long as arbitrary large values of m and n can be chosen, so that our condition must satisfy. That means, modulus of x n minus x m is greater than or equals to epsilon naught. Now, let us start with some theorems related to the Cauchy sequences. Our first theorem is, if x is equals to x n is a convergent sequence of real numbers, then the sequence x is equals to x n is a Cauchy sequence, or in other words, we can say that every convergent sequence of real numbers is a Cauchy sequence. Let us start with the proof. As given, the sequence x is equals to x n is a convergent sequence. If it is convergent, then the limit of x n must exist. Let us say limit of x is equals to limit of x n is equals to x. So, x is a limit of the sequence x n. Then, by the definition of convergence of sequences in real numbers, we can say that for every epsilon greater than 0, there must exist a natural number k. depending upon some epsilon. In this case, we choose our epsilon as epsilon is equals to epsilon upon 2. So, by the definition, there must exist a natural number k depending upon epsilon upon 2 such that for all natural numbers n greater than or equals to k, where k is depending upon epsilon upon 2, we must have modulus of xn minus x is strictly less than epsilon by 2. Say this is our equation number 1. Thus, if we set our natural number h which is depending upon epsilon as h is equals to k, and for all natural numbers n and m greater than or equals to h, then we have modulus of xn minus xm. Now, add and subtract x in this equation, we get equals to xn minus xm plus x minus x. If we rearrange these terms, we get modulus of xn minus x plus x minus xm. Now, applying triangular inequality in this equation, we get modulus of xn minus xm is less or equals to modulus of xn minus x plus x minus xm. As from equation number 1, we get xn minus x is less than epsilon by 2. So, if we substitute the values of this, then we get this term is less than epsilon by 2 as well as this term is less than epsilon by 2. That means, modulus of xn minus x is strictly less than epsilon by 2 and xm minus x is strictly less than epsilon by 2. So, our equation becomes modulus of xn minus xm is less than epsilon. Since epsilon greater than 0 is an arbitrary number, so we conclude that if xn is a convergent sequence of real numbers, then x is equals to xn must be a Cauchy sequence. Now, we will establish our next result. Our next result is every Cauchy sequence is convergent. So, for that, let us suppose x is equals to xn be a Cauchy sequence of real numbers. We need to prove that this sequence is bounded. Let epsilon is equals to 1 in this case. Obviously, 1 is strictly greater than 0. If h is equals to h and this h is depending upon epsilon, and in this case we choose our epsilon is equals to 1. So, if h is equals to h where h is depending upon 1 and all natural numbers small n greater than or equals to h, we have modulus of xn minus xh is strictly less than 1. We can consider this equation because given in the statement as our sequence is a Cauchy sequence. So, by the definition of a Cauchy sequence, we can say that for all natural numbers n greater than or equals to h, we have modulus of xn minus xh is strictly less than 1. Hence, by the triangular inequality, we can rewrite this equation as modulus of xn is strictly less than modulus of xh plus 1 for all natural numbers n greater than or equals to h. Say this is our equation number 1. Equation number 1 is modulus of xn is strictly less than modulus of xh plus 1 for all n greater than or equals to h. Now, if we set capital M as capital M is equals to supremum of all the numbers, and the numbers defines as supremum is equals to x1 comma x2 comma x3 up to modulus of xh minus 1 and modulus of xh plus 1. If we set capital M is equals to supremum of all these quantities and say this is our equation number 2. So, from 1 and 2, we can easily say that modulus of xn is less or equals to m. Our equation number 1 says that modulus of xn is less than modulus of xh plus 1, and from equation number 2, we say that this whole quantity is equals to m and m is equals to supremum. So, we get modulus of x n is less or equals to m for all natural numbers n. Hence, we can say that a Cauchy sequence of real numbers R is bounded. Now, Cauchy's convergence criteria. The statement for the Cauchy's convergence criteria is a sequence of real numbers R is convergent if and only if it is a Cauchy sequence. I repeat the statement of Cauchy's convergence criteria. A sequence of real numbers R is convergent if and only if it is a Cauchy sequence. We will do the proof in next lecture. Thank you.